Ho, ho, ho.
Hi, welcome. I'm here with Ricardo and Anna, and today we're going to talk about our final project.
Our objectives for this final project were to build a homemade Michelson interferometer that could produce high danger fringes and using these fringes to measure the wavelength of a red laser.
For the theoretical framework, we've already worked with a Michelson on the lab. However, this is the general arrangement of one. We have a pointed source that is going to be inciding to a partially reflecting surface. One is going to get transmitted, the other one is going to get reflected, and these two mirrors over here are going to bring them back, and they're going to be superimposed in some point of our vision screen. It is important to comment that in our interferometer, we make one arm bigger than the other. So then we define D as just the distance between those mirrors that is can be calculated by just subtracting these two magnitudes. When we do that, we can transform this diagram in a linear one where we can think the virtual sources as these planes over here. This model is going to help us make the geometrical analysis of the interferometer easier.
As my partner Diego said, making our arrangement in this way is going to let us analyze better our Michelson interferometer. Here we have the source, and here our two reflected rays are going to be appearing coming from these two virtual sources. These two virtual sources are going to be separated by a distance 2D, since the difference of distance between the two mirrors from the beam splitter is D, and the light travels two times through it. We have this distance equal to 2D. And this subtended angle theta, it's going to be the one that determines the difference of path. So as we can see from this geometrical analysis, this path difference is going to be approximately 2D times cosine of theta. And then to make this our phase difference, we're going to multiply by k and also add this phase shift of pi that my partner mentioned earlier. So for our destructive interference conditions, we have the same condition as always. So just substituting this equation and this equation, we can clear for this condition for destructive interference. And as we can see, if we substitute theta equal to 0, meaning that the m sub 0 is going to be 2d over lambda, and this number is going to be a really, really huge number associated with the central minimum um, of the pattern. So my partner Diego is going to explain to you how are we going to use this m sub 0.
So we know that we have this number associated to this central minimum, and we want to pattern this whole, to map this whole pattern. Then if we want to go from the central minimum to another minimum, then we just have to add or subtract a wavelength if we're gonna go up or down. So then for any given p range, we just have to keep adding multiples of lambda. So then we can find this expression over here. Now, when we substitute this expression of m0 in the equation, we can obtain this equation. And this is a really convenient equation because when we approximate theta p to 0, meaning we are on the paraxial regimen, then we can Taylor expand this cosine to the second order term and substitute here. Then in the paraxial regime, we can say that theta p is just this expression over here. However, notice that theta p, as defined in this triangle over here, we can think it as this triangle over here. So then we can think of the as a sine where the opposite side is the distance between the minimum maximum to any given dark fringe. And L is going to be the distance from the beam splitter to the vision screen.
Okay, so the materials and the methodology for this experiment included a magnifying glass and some non-magnifying glass, that's just normal glass, two mirrors, a red laser with a wavelength between 630 and 670 nanometers, a protractor that we just printed in a sheet of paper, a flexometer, and graph paper.
The methodology to build the Michelson interferometer consists on fixing the laser point on at a certain height, align the magnifying glass, then align the beam splitter, then first align the mirror for the transmission arm, and last align the mirror for the reflection arm. This was the experimental setup that we used to build the interferometer. We use materials that we found on our home. We use something to hold the magnifying glass. In this case, was a Nerf gun that we had. We use some cloth pin to hold the mirror and the beam splitter. We also use a mirror that could change the angle. We place the beam splitter in the protector, and we aligned it with a flashlight that we use the shadow to make sure that it is a 45-degree angle from the laser point. We use a deck of cards to change the height of the laser and some hair bands to hold it in place. In that picture, we can see the Michelson interferometer from the point of view of the screen, and we can see the virtual sources that my partners mentioned.
So with this interferometer, we were able to obtain this interference pattern. However, notice it is a moving interference pattern because we built the Michelson on the ground, and the ground is always moving due to mechanical waves or people walking or stuff like that. So then we didn't have a fixed interference pattern to analyze, and we really needed to make them stop in order to actually measure things. So what we did is that we took a bunch of pictures of the pattern moving, and then we chose the pictures where the central minima was more clear to see, and we then selected these pictures to be analyzed.
So for the analysis, we use these equations here. This is the one that we cleared for lambda. Here's how we obtained the error for lambda, and this is how we propagated the error of d.
For the first photo, we could see 7 dark fringes, and we measured the values of the A sub p, and with the equation I mentioned, we calculated the lambda. We then obtain a measure of the average of lambda, and we can see that in this particular photo, that value wasn't in the interval that Anna mentioned. For the second photo, we could also see 7 dark fringes. We can notice that this average was in the interval. For the third photo, we could only see 6 fringes. And this lambda was also in the interval I mentioned. And the error of the average was obtained by calculating the standard deviation of the data divided by the square root of the number of data.
For a quick discussion, we can see that on the first photo, we didn't get a value in the interval. However, we can see that it is the less clear on the minimum. So it makes sense that we get some value that is not in the interval. For the second one, we did get some values, but then we did have some errors, like somewhat big. Of course, this is hard to make because we are working with a pattern that is always moving, right? So then these errors make sense when we are working on a homemade equipment like this, especially a very sensitive equipment, since any given little movement, we could either lose the pattern or just, yeah, it was hard. But we did get some approximations that were in the interval, so we can say that we were able to somewhat approximate the wavelength. So that's it. Thank you so much and happy holidays.